Welcome back all of you. So today we'll start the new type of renewable resource, that is biomass, and lecture content for today would be the definition of biomass. What does it mean according to different protocols or different agencies which are followed internationally? Then different sources of biomass and the potential, maybe the global potential as well as the potential in India. This will be followed by some properties of biomass, the types of biomass, and different types of common analysis that we use to categorize or classify or to find the composition of the biomass. And finally, we will look at a small numerical on how to derive the molecular or the empirical formula of any given biomass based on its elemental composition. So, what is biomass? IEA, International Energy Agency, it defines biomass as any organic matter or a biological material which is available on a renewable basis. So, we can think of organic matters which contains mainly the hydrocarbons, and they are basically derived from the biological sources. For example, plants, animals, human beings, the waste products coming out of these species. So, all those things are biological material, the material which comes from biological organisms, and they are available on a renewable basis because they get replenished in years, sometimes days, months, years, or even decades. If we talk about a big forest or a big tree, if we cut it down, it will take 30-40 years for that tree to grow back to its original shape and size, right? But again, it is able to grow on a renewable basis, unlike fossil fuels, which takes like a long time, like more than thousands and millions of years to get replenished. So, it includes feedstock derived from animals or plants such as wood, agricultural crops, and organic waste from municipal and industrial sources. There are many things which comes from the municipal solid waste or industrial waste which are of biological origin. So, they are also classified as biomass. Industries, for example, rice mill, sugar mill, okay. There are many food processing industries which will generate the waste which are of biogenic origin. Municipal solid waste, though the major components would be paper, plastic, cardboard, but there is a significant portion which occupies the biodegradable matter, and that biodegradable or organic portion of MSW is nothing but biomass. There is another definition by BSI, British Standards Institution, which says biomass is a material of biological origin, excluding material embedded in geological formations and or the fossilized. So, all those materials which are there in the rock formations, in the geological formations, or in the form of fossil fuels. Excluding all those material, rest of the materials which are coming from biological origin are called as biomass. This definition is also correct because unless the timeline is clearly mentioned, even the geological or the fossilized material is of biological origin. It's when a plant dies or animal dies, and when it gets decayed and goes back into the soil over a period of time, it's the same material which will get fossilized, but the time duration is extremely long, so we don't call it as a renewable basis replenishing material, okay. So, they define it like this, but the common book definition or the one which is followed by IPCC is, so biomass is biological or organic material which is derived from living or recently living organisms, including plants, animals, and microbes. So, the moment it mentions recently living, it means it includes dead material, but not the dead material which has been staying idle for thousands or millions of years, like in case of geological formations or the fossilized material. So, this definition is much more easier to remember and more holistic, which covers biological material, organic material, and which is derived from living material, okay, or living organisms or a dead organism, but which was recently living, and it includes plants, animals, and microbes. So, if you look at different sources of biomass, we can get it from agriculture, forest, then municipal solid waste or municipal sources, industry sources, even sewage sources can also give us biomass. So, these are categorized in these 6 forms you can see here. The first one is agricultural and crop residues. Most of the biomass or the lignocellulosic biomass that we talk about comes from the crop residues or the agricultural sources from the farms. Second is forestry, crops and residues. So, after the trees are cut for say timber or wood, there is a lot of slash like branches, twigs and leaves waste which are lying down in the forest, or the dead trees or the old trees which are cut down for energy purposes. And then there are many crops or plants and trees which grows in forest which can provide biomass. Industrial residues, mainly food processing industries or the mills like rice mill, sugar mill, they will also supply biomass. Animal residues, here more than the, it's not about living organism, but it's mainly the excreta of animals such as poultry farm or dairy, or even dead animals can be accounted as for the biomass from animal residues. The municipal solid waste will account mainly for the biodegradable or the organic portion of the total solid waste that is generated in the municipal areas or the residential areas. Sewage, it comes mainly from in the liquid form, but then there are lots of solids in that liquid sewage. So, when that sewage is treated in a effluent treatment plant or a sewage treatment plant, all this organic portion which can constitute the biomass is separated as sludge, and that is also a source of biomass because the capacity of STPs are huge and the flow rates of water which goes into the STP on a daily basis is significant. It's in million liters per day. So, these are different sources of biomass, and if you look at some specific examples, forestry crops, they include firewood, pine needles, wood chips or logging debris. Then agricultural crops, like residues from different crops which are grown in the farms. Algae can be included in agricultural crops and residues because that's the best amongst these categories where we can put algae as a plant. Municipal solid waste, biogenic waste, paper, cotton, wool, food scraps or leaf litter. Animal residue will include manure and human sewage and dead animals, and industrial residues will include the carpentry industry waste, dairy, sugar industry, textile industry or black liquor. So, all those things are the examples of different categories of biomass sources. Now, how much biomass do we have in this world, and what portion of it can we actually use for energy purpose or for other purposes? So, global energy demand, because this is a course on renewable energy, let's focus mainly on energy. Global energy demand is approximately 508 exajoule per year. Okay, exajoule is like 10 to the power 18. 1 exa is 10 to the power 18. This is the global energy demand. And photosynthesis, which is a main process to capture solar energy into the food or into glucose through plants, it captures 3000 exajoule per year, of which humans are exploiting or using 10% of it. So, 10% of 3000 is 300 exajoule. Now, out of this 300 exajoule which is used, 230 is used for primary needs like satisfying our food, fiber demand and bioenergy. 70 is lost annually during harvest or through open burning or field fires. Okay. So, out of 300 exajoule, we are able to use 230 exajoule. And this is the reason why any bioenergy projection which is exceeding 250 exajoule per year, it is not feasible practically because it surpasses the Earth's natural biophysical limits. It is not possible to extract energy more than this value from biomass, as it will disturb the geological or biophysical balances. So, at present, if we look at the total primary energy supply which comes from biomass or bioenergy, it is around 10% of global primary energy supply, but most of it is in the form of heat. And out of the global renewable power capacity, only 4.4% is coming from bioenergy. So far as power generation is concerned, the contribution of biomass or bioenergy is much lower compared to solar and wind and hydro. If you look at the biomass potential in India we have huge amount of crop residues and then other biomass coming from forestry or industrial sources, which ranges from 500 to 700 million metric tons per year. This is the gross generation, and out of this biomass, most of it is used, but there is surplus availability which is around 230 to 280 million metric tons per year. And this surplus means the biomass which is used for cattle feed, compost or domestic heating for traditional uses, that has been subtracted. So, this is what is remaining in surplus, which can be used for power generation or for other energy purposes. So, at present only 120 to 150 million metric ton is utilized for energy. So, there is still a huge scope to increase the consumption of biomass for energy, and India has more than 30 states. So, amongst them the leading states which has huge sources of biomass are UP, Maharashtra, Madhya Pradesh and Punjab. UP, it is the most populated state and spread across a wide region along the Ganga river. So, the soil is fertile and is a huge agricultural production which results into the generation of huge amount of crop residue. Maharashtra and Madhya Pradesh also have a huge amount of agricultural land and some forestry area which generates, and they are also populated, followed by Punjab, which has one of the best irrigations and dams and canal facility, which is promoting the rice and wheat growth in the state significantly, and then the rice straw or the paddy straw or the wheat straw which is grown in Punjab is in abundant quantity. So, when it is concerning the power generation, the present installed capacity for bioenergy is around 11.75 gigawatt in India, and more than 90% of this is actually coming from sugarcane bagasse cogeneration plants. So, in the sugar mills, typically the energy which is required by the mills is self generated. They use the bagasse which is left after the juice is extracted, mainly in gasification plants or mainly in the CHP, like combined heat and power plants. So, they are able to produce heat and generate some power. The theoretical bioenergy potential is around 43 to 50 gigawatt. So, in terms of power generation, like in terms of promoting biomass for power generation, there is still a long way to go, and we can expand this capacity by 4 times. So, why is biomass special? Like, what makes it different from other renewable energy sources? Obviously, like the word biomass, it means bio means living, mass is the weight of that living organism or the product derived from that living organism. So, unlike in solar, wind, hydro, which are the other renewable sources, they can provide only energy. Biomass is one source which can not only provide us energy, but also the material or the mass, and lot of materials or objects which are otherwise made from fossil fuels can be made from biomass, and they can replace the fossil fuel in the material domain also. So, that is why biomass is a special renewable energy source. Material provision, it is the only renewable source that provides material for plastics, chemicals and textiles in addition to energy, right. Solar, wind, hydro, they cannot provide physical material for any industry, they can provide energy. Energy storage, biomass, because they work on its stored chemical energy. So, it has a built-in energy storage in the form of chemical energy, which is stored in the organic bonds of the material, and it is that energy which is used when it is converted to some other form like heat or electricity. Solar, wind and hydro, the other renewables, they need external energy storage like batteries or pumped hydro or hydrogen storage, because they can provide a source only to generate the electricity or generate energy, but to store it we need some other equipment. Then so far as grid role is concerned, biomass can be used as a base load or in the form of dispatchable mode, as they can provide steady 24/7 supply and ramp up on demand, because just like coal, biomass can be stored at a location depending on the the energy requirement. Other renewables, they are intermittent and variable, so they depend on weather or seasonal water flow, excluding large reservoirs. So in hydro, when we have huge reservoirs or like big dams which stores lot of water, so there we have more dispatchable or more reliance on base load. But for small hydro or for solar and wind, it's mostly intermittent and variable. Carbon profile, biomass has the potential to go from neutral to net negative also, and it is the only source which is capable of atmospheric carbon removal by BECCS, which is bioenergy with carbon capture and storage. And other renewables, they can go as high as up to carbon neutral. They can achieve close to zero emissions during operation and neutral emissions over the entire life cycle. But biomass, because while the biomass is growing, it takes CO2 from the atmosphere for its growth, right? And this absorbed CO2 is stored in the biomass as a chemical energy, and it's the same energy which is released into the atmosphere. So we are not adding any extra CO2 in case of biomass. So biomass is inherently like a carbon neutral. But now while processing that biomass, if we are able to generate energy and the same amount of energy is being substituted by substituting fossil fuels, so it can provide us like net negative potential, or it can, the net emissions can be negative. Similarly, if we produce products like biochar and put it deep into the ground, the solid the carbon which would emit into the gaseous form after combustion, now it is stored in the solid form which can stay for centuries. So we are doing additional carbon removal via carbon capture and storage. So it has a net negative carbon profile. Physical state, biomass is highly versatile for transport, heat and power, because it is a solid material. It can be converted into the liquid biofuel or solid fuel, and it's easy to transport, store or consume. Solar, wind, hydro, we cannot carry them, so we need to convert it into electricity or heat first, and then they can be used. Main constraint for biomass is the need for land, the logistics and resource sustainability. Logistics, because biomass is a highly heterogeneous and scattered resource. It is spread over the like a huge region, and to be able to use it, it needs to be collected, harvested, then maybe it needs to be stored and shipped across long distances depending on where is the processing unit or where is the end use requirement. Whereas in other renewable cases, they also depend on geography and weather, but they will require mainly the minerals to construct the equipment that would tap this kind of energy. For solar, we will need PV modules or solar thermal collectors. For wind, we would need huge wind turbines. So for them, there is a lot of requirement of minerals. For hydro, we will need a precise geographic location with lot of water availability, and then the materials for constructing turbines, dams, penstock, so all those things. Now, biomass properties and types. So there is a range of different values or different properties for most of the biomass. So the first one, it is given in the form of proximate analysis, where its moisture content ranges from 5 to 60%, ash content 0.5 to 20. Generally the woody biomass, they don't have much ash, but something like rice husk or to say rice straw, they will have huge amount of ash, up to 15 to 20%. Volatile matter, it's 60 to 85, and fixed carbon is around 10 to 25. It is this fixed carbon which stays in the biomass when it is converted to, let's say, solid product called biochar, which can be used for storing carbon underground. Calorific value ranges from 10 to 25 megajoule per kg. Bulk density, it varies from 40 to 800, because it depends. Like if we talk about a biomass like hay or a paddy straw, which is very loosely packed, so the bulk density would be very low. But something like coconut shells or walnut shells, which are heavy, brittle, strong and solid, they will have much higher bulk density. Particle size, this is the typical range of particle size. We can have more than 10 centimeter size particles, but then they will have to be crushed to at least less than 10 centimeter to be able to use in different types of reactors. Biodegradability. Now there is two types of biomass, like high moisture and low moisture. So generally for food waste and manure type of biomass, which is used mainly for biochemical conversions, where we rely on microbes and enzymes to degrade those biomass. So there the biodegradability is high. Whereas for woody biomass, agricultural or forestry biomass, which are mostly dry, they have low biodegradability. And renewability, all the biomass, they gets replenished within months to years. Now, so far as types of biomass are concerned, there are two broad types. One is lignocellulosic, another is non-lignocellulosic. About 80 to 90% of total biomass in the world is under the category of lignocellulosic biomass. Lignocellulosic means it contains lignin, cellulose and hemicellulose, and non-lignocellulosic will contain carbohydrates, proteins, fats, lipids. So this biomass, lignocellulosic biomass, they includes mainly wood, straw, grasses, leaves. So herbaceous biomass, the grass, shrubs, then agricultural biomass, forest residue, crop residue. Non-lignocellulosic biomass, they occupy only 10 to 20% of total biomass, and they include animal waste, manure, sewage, sludge, food waste, algae, oils, protein, sugars, all those things. Let's look at one by one both types of biomass. So lignocellulosic, if you look at average composition on dry wet basis, the typical range is 35 to 50% cellulose, 20 to 35 hemicellulose, and 10 to 30 is lignin. These are the major components, major organic components. Then we have some extractives and some ash. Ash is mainly inorganic components into the biomass existing as minerals. And extractives are mainly the fats and oils or waxes, resins, gums like material, which also happens to appear in some of the lignocellulosic biomass. If you look at a structure of a plant cell wall, if you zoom it on the cell wall, you will see hemicellulose, cellulose and lignin existing in this form, where the walls of the cell, actually this is lignin, and this green structure, green lines, these are cellulose, and these thin threads, they represent hemicellulose. So just looking at the structure, you can tell that hemicellulose would be the one which would degrade first, followed by cellulose and lignin. Lignin has a huge decomposition range, as you can see from the structure. Hemicellulose and cellulose, hemicellulose, they are mainly the branched polymers of different sugars like xylane or xylose. They are less crystalline and they are easy to decompose, whereas cellulose, they are a linear polymer. You can see it is a linear polymer of glucose. It is crystalline and difficult to break down compared to hemicellulose. Whereas lignin, this is one phenylpropane unit. It is a complex aromatic polymer and it is difficult to degrade and it has high heating value. So whatever solid fuel we are getting from biomass, it will be mainly because of lignin, and whatever gaseous fuels we are getting from biomass, main contributors would be cellulose and hemicellulose. Non-lignocellulosic biomass, here we don't like bifurcate the composition in terms of lignin, cellulose and hemicellulose, but then there are other terminologies like proteins, lipids, carbohydrates. Okay, so proteins are around 20 to 30%, lipids 15 to 25, and carbohydrates 20 to 35%. And then this biomass also may have some ash, water, and others. So this should not be on the dry weight basis because it shows 10 to 20% moisture. These are the structures of carbohydrates, proteins, fats, and lipids. We won't go into extreme details of it, but what you can see here, carbohydrates, they are like the polymers of monosaccharides. So they are called as polysaccharides. They store energy. Okay, and in structurally they appear to be looking like a polymers of glucose or cellulose. Proteins, they have peptide bonds, and they are composed of mainly the amino acids. Okay, so they will have primary, secondary, and tertiary arrangements of different molecules of amino acids, and their role is mainly biological catalysis and cell structure. Carbohydrates are mainly for energy storage. Fats, they are for long term energy storage. So you can see the molecules with double bonds exist here in the form of triglycerides. And lipids, their role is to form cell membranes and insulation. So like in the lignocellulosic biomass, what role is done by the lignin, similar role is done by lipids in non-lignocellulosic biomass. These are some of the examples of non-lignocellulosic biomass like bone, algae, hair, sewage sludge, meat, feather, and manure. So now that we have seen different types of biomass based on their composition, mainly lignocellulosic and non-lignocellulosic, there are different types of analysis which we can do to identify compositions of biomass. So first is biochemical, second is proximate, and third is ultimate. So biochemical analysis, it tells us the fibrous or non-fibrous composition, mainly cellulose, hemicellulose, lignin, protein extractives. Okay, and proximate will tell us fixed carbon and volatile matter, moisture, and ash. Ultimate analysis tells us elemental analysis, CHNSO, and it will be, if it is on the dry basis, then moisture and ash will be taken off. This is the biochemical composition, which is done mainly by following enzymatic processes or enzymatic approaches. Proximate ultimate analysis, and the heating value, grindability, work density, they are done by thermochemical analysis. So these are intensive properties and these are summative properties. So biochemical analysis determines chemical or biochemical constituents of biomass, cellulose, hemicellulose, lignin, and if it is a non-lignocellulosic biomass, it can tell us proteins, lipids, carbohydrates, and extractives. Proximate, it tells us major physical fractions of biomass, it is moisture, volatile matter, fixed carbon, and ash. Ultimate, it tells us elemental composition, carbon, hydrogen, nitrogen, sulfur, and oxygen is found by difference. And the common methods which are used for these three analyses are given here. So biochemical analysis, we do it use following Van-Soest method. Here actually we follow 3 steps to determine 3 types of fibers, like one is NDF, ADF, and ADL. So NDF is neutral detergent fiber. It tells us the total insoluble fiber composition of the biomass, which includes all 3, hemicellulose, cellulose, and lignin. Then acid detergent fiber tells us like least digestible portion of the biomass, which is cellulose and lignin. And this acid detergent lignin will tell us indigestible portion, mainly the lignin part. And then based on the 3 following mathematical equations, we can get individual composition of cellulose, hemicellulose, and lignin. TGA, it's called as thermogravimetric analyzer. The name of equipment is thermogravimetric analyzer and the process is called as thermogravimetric analysis. So based on the mass loss of the biomass sample, the first moisture is released, then volatile matter is released, then fixed carbon is released, and finally remaining is ash. So we get the proximate analysis. CHNS analyzer, it's a highly sophisticated equipment where you put the sample and it will give us these 4 material elemental readings, and then we subtract ash out of total mass. CHNS 100 minus CHNS minus ash will give us oxygen. So, oxygen is found by difference. Proximate analysis, like I said, it's based on the mass loss curve. So, when the sample is put into the thermogrametric analyzer, initially the mass is 100%. As you go on increasing the temperature at around 100 degree, you will get the moisture. When the temperature is increased all the way to, let's say 700 or 500, so volatile matter is released, and at this point where we have got moisture and volatile matter, this process is happening in inert medium, typically nitrogen. At this point, if we inject air or oxygen, the fixed carbon portion will start to burn, leaving only the ash at the end. So, that is how proximate analysis is conducted using a TGA. This table shows proximate analysis of some of the species found in India like bamboo, gulmohar, neem, and you can see most of the biomass, they have high volatile percent, 80%, ash in the range of 4 to 5%, and fixed carbon in the range of 12 to 15%. This is example of date palm tree, and the heterogeneity in biomass is so much that even for the same tree, different parts of this tree will have different biomass composition, and the different trees at different locations can also have different composition because it changes with location, climate, age and soil. Then biomass values, hence it is often reported as ranges or the average values, and they are not reported in single numbers. Proximate analysis from this paper, it shows for a date palm tree, for seed, leaf and stem, you can see stem has very high moisture, less volatile, high ash compared to seed and leaf, which has very low moisture and ash but very high volatile matter. Similarly, in ultimate analysis, you can see leaves have highest carbon followed by seed and then stem, and these are the other components. Let us do one numerical. It will tell us how we can derive a molecular or an empirical formula for any given biomass. So, when you subject a biomass sample to ultimate analysis, we can get its elemental composition, moisture and ash. So, the same is given to us in the question, biomass sample composition on mass basis on received basis. Received basis means the way the sample is brought to us. Okay. There may be other bases like say dry basis, so we will neglect moisture content in it. If it is dry ash free basis, we will neglect moisture as well as ash. So, carbon, hydrogen, oxygen, nitrogen, sulfur is known, moisture and ash. Addition of this, I think it comes out to be 100. So, it is on the received basis including all the possible components. Find the molecular formula on received basis and on dry and ash free basis. So, first we will just find a formula for this composition on received basis. These are the atomic weights of the compounds. So, carbon, hydrogen, oxygen, nitrogen, sulfur, these are universally like known, 12, 1, 16, 14, 32, water is 18. Ash is something which needs to be given in the numerical because it will change with different biomass. So, ash is 56. The formula for finding number of moles is mass in gram by molecular weight, right. This is the only formula that we will be using in this numerical to solve the problem. So, for questions like this, we start always with the basis. So, first basis is, let us take 100 gram biomass as basis. So, all these percentages would be converted into grams. So, carbon to moisture, they are converted to grams. Now, the first part is we have to find it on the received basis. So, let us convert this ultimate analysis in grams to moles. How will we do it? We will just divide each of these atoms by their atomic weight. For moisture, we will use 18, for ash, we will use 56. So if you draw a table like this, components, list down all the components, the masses were known to us from the question and the given data. Now we divide each of these components by their atomic weights to get gram per mole. Okay, sorry, these are the atomic weights or the mass, and number of moles would be just 37 divided by 12, that is 3.1, 8.8. So we just divide this by atomic weights and we will get the molecular formula. This molar coefficients of each component gives us the molecular formula in this form. Now here you can see water is 1.1389, but since it consists of H2 and O, we can add hydrogen and oxygen into these components. So that's why, so this 8.8 plus, so H is actually 8.8 plus 1.13 into 2. So this gives us 11, and O is 1.7 plus 1.13, so it is 2.86. So we have accommodated hydrogen and oxygen of water into the same formula. So this is our molecular formula on residue basis. It's not wrong if you write H as 8.8, O as 1.7, and then mention here H2O separately as 1.13. This is also fine. But then since we are talking about molecular formula at atomic level, we can include O and H of water in the same formula. The second is dry ash free basis. So we will remove the moisture and ash portion. So out of 100, moisture and ash 20 and 5 is removed. So what we are left with is 74.4 gram. Now with respect to this new mass, let's find the new percentages of CHONS. It will be like initial was 37.5. Now 37.5 was in 100 gram, but on dry ash free basis 37.5 gram is in 74.4 gram. So the weight percentage will change. 37.5 by 74 into 100, it gives 50.4. So the new percentages of CHONS would be 50, 11. They will just increase by a certain fraction. Since we are doing it on dry ash free basis, we don't need to include water and ash in this table. Once we get the new masses based on new percentages, we divide it by their atomic weights to calculate number of moles, and these molar coefficients will give us the molecular formula of biomass on dry ash free basis. Now this is on residue basis, this is on dry ash free basis. But if we want to convert it into an empirical formula, we can just do it on the basis of, or normalize it on the basis of carbon. So if we normalize this, both the formula with respect to carbon, the empirical formula would be CHONS. So the second case, if we divide 3.125, that's the mass of carbon. So by that number, each of these numbers would get divided, and that will give us the empirical formula on dry ash free basis. If we do it for here, it will give us on the residue basis. Okay. So that's how we can derive the molecular formula of any given biomass based on the given composition. So to summarize, we started with biomass, the definitions given by different agencies at international level, sources and potential, like what are the different sources of biomass, like industrial, agricultural, forestry, municipal, sewage, animal residues, okay, and the potential, like the biophysical limit, then availability in India. Then we looked at different types and properties and analysis of biomass. In types, there were mainly two, lignocellulosic biomass and non-lignocellulosic biomass. Properties, we looked at different range of values for different types of biomass. In analysis, we studied mainly proximate, ultimate and biochemical analysis, okay, for cellulose, hemicellulose and lignin. And finally, we looked at a numerical and learned how to derive a molecular or empirical formula for any given biomass based on its ultimate analysis or elemental composition. So with that, let's stop here. Thank you so much.